Alright, welcome back on Stokes Theorem. So I just make another video so then um, you can make it make your work easier because you want to learn something, one thing, another thing. Just for your information, so the green theorem, I put it into assignment for your continuous assessment. I mean for your assessment. But for Stokes theorem, I give in final exam question. So I hopefully this lecture will help you a lot to understand and also to help you ease your understanding on Stokes theorem for your final exam preparation. Okay, Stokes theorem. As I said previously in our last lecture of green theorem, so Stokes theorem basically wait, I want to check. Good. Stokes theorem basically um, do integral a integral trick to make your life easier to understand to calculate in three-dimensional things. So basically, if you understand that, if you remember that green theorem involved the curl, which is the same thing for the case of Stokes theorem. So, but for green theorem, we didn't have in Z component, so your life easier. It's only involved in two part. But for this one, we have a three real space defined. It is not a tree, but we try to understand how to make it easier. Suppose now we have a vector W in R3, vector field real space of, which is S, and S is a surface. Then we wish to explore the curlity of the vector field within the surface part. The reasonable guess based on our experience from previous, it should be like this, which is the same thing, which is now the boundary is become a space surface boundary. The previous one in green theorem, we use a boundary in Q, which is a rectangular domain. This turned out to be the case, is called a Stokes theorem. We will not prove it here. It is quite similar to green theorem. The strategy is once again to choose a lattice point and so on into a bunch of parallelogram. Then we chase through the definition on each. At every parallelogram, we see that we get the same integral W over the boundary of the parallelogram. But because of the orientation as consideration, the integrals over the boundaries of neighboring parallelograms cancel. The result is the integral W over the boundary of S. Yeah, this one is quite it's more or less is a concept. One potential complication is using Stokes theorem is determine the boundary of the S in question. So it is difficulties of using Stokes theorem. We need to determine what is the boundary surface. So for example, this is the boundary surface. So you have a normal vector which is of the cross W of the nabla. So will give you definitely another field of another orientation of the vector field, which is a normal vector field over the domain of surface. To get the proper orientation of boundary S, you need to know the orientation of S. Recall this is often given an outward pointing vector. So now this is your pointing vector. To get the to get the orientation of we use the right hand rule. So you use right hand rule to do this point the thumb. Okay, it is just like a torque Q of FR, right? So when you have two cross vector, so you get another dimension of vector field. Your finger with the curl of the sense of determine the orientation of the boundary. So this is Stokes theorem. So you need first determine Stokes theorem of the boundary, the surface boundary. Okay, let do some example, which is quite I think straightforward. Which is all the rest I just give the example. So this is the simplest one, is the first one here. So let's say we have S of the surface denoted on the top half of the unit sphere. So you have sphere on the back side, inside the one. So you have the ground. Okay, right. With the orientation given by a vector. So now your vector is x 0 0. So you have normal vector. So definitely here, so your normal vector of 1 0 0 at the point 1. So point here also 1. So this is point 1, x1, y0, z0. So meaning that if we have this is quite difficult, because this is the first drawing is I just draw it without any scale, or what we call it, scale, and also without any real scale, or without any real axis or point. So if we have point 0 0 here, if you want to make it easy understanding, so your point 1 0 should be here, and also if z here also as well. So it is in 3D. So we start something like this in 3D. So the structure will be like that. So this should be a real one, because we have the real axis, and also the structure is, because the figure is quite easier to understand. It is very understandable. So first, okay, this one. So you should, I just put this everything here to make sure we can understand how the structure looks like, because it's not given in the figure. Use Stokes theorem to integrate the curl. See, vector field of x over the domain of S is given. Domain itself is given in as top of sphere, top of unit sphere. Top half of unit sphere is a given domain. Okay, and it's being parameterized. So as top of half unit sphere. So half unit sphere, you have the domain of 2 pi. So everything here is 2 pi. Right, something like that. Everything should be in circular part. So you have the domain of S from 0 until 2 pi, because it's a spherical grounding. Okay, so you have a vector field. So you have a vector field of yx. So your W will be negative yx 0. So if you notice here, your W is now lies only on the two plane, right? Two-dimensional plane. First, we take a Stokes theorem. Stokes theorem say the answer will be the same as the integral, right? So this is the Stokes theorem say around the S boundary with a propagation parameterized, so your parameter is called sine, and also no parametric on the Z component. So actually it's quite straightforward. Okay, first we take the step do is we need to simplify. I mean, we need to find the cross of W, the cross product of W of the vector field W negative Y X, and parameterized by psi. So so you have d psi over dt. Okay, so now the part the integration part of omega W parameterized by t is given like W is equals to what will be your W, negative Y, what will be your negative Y, negative sine t, and then X, what will be your X, cos t, and 0. So this is your W, correct? And also your d psi over dt, for this one, if you differentiate cos, you get negative sine. If you differentiate sine, you get cos t, 0. Okay, so this is your d psi over dt. Okay, so over the domain of S is your 2 until 2 pi. So then, because of your identity, you multiply here, so you get the identity of 1, so you get sine squared pi cos squared t, which is this identity equals to 1. So you put it here, 1 dt, so you get 2 pi. This is really quite simple, but again you need to show the step to prove to get the full marks of your work. Okay, so that first example, which is quite simple, and hopefully this example make you much more easy to understand. So next to the real part, which is the applied one. So just for the split for the case of understanding, we can make it much more easy to understand. So the example is to calculate the Stokes theorem. Stokes theorem for the field of vector f. So this one use another notation. We used previously W. So now here they use F. It's okay, which is the same thing. I mean the same step. On the ellipse of S. So now the domain are different. So because it has ellipse as a domain. So now the domain becomes x squared, y squared, which is a circle, something like that, at z equals to 0. So first we the space or the curl of the domain is within the ellipse, right? So ellipse is your container ataupun boundary. It's a boundary. So we start compute the circulation of integral of ellipse. X squared plus y squared divided by 2 squared equals to 1. This is the formula. So the ellipse, it is not a circle. The ellipse is something like ellipse ni more or less is kind of the lonjong. So that's why normally for circle x squared y squared equals to 1, but for ellipse you have squared here. So this it shows you on the the y dimension, on the y space, the value are differ. It's not equal to the x. This is x component, right? So 1 no, it's now becomes 2. So this is your r. So we need to choose the counterclockwise parameterization, hence the normal to s is point outward. So the normal is given is positive direction. So because of positive direction, the direction of our circular the ellipse part in right hand rule, using right hand rule, so is on the anti-clockwise direction, anti or counterclockwise direction. So for parameterization, so you have cos t to sin t. Normally if you use for circles, you have cos t sin t. But for ellipse that have two magnitude of 2 on the y component, so it's become 2 here. Therefore the right hand rule normal is right forward. So this is x, y and z. So this is the vector z. This is not a point, so this is which is a vector on upward, on which point is it doesn't affect anything. What point you have, which point n will be here as well, and can be here, and can be something somewhere, but the magnitude equals to the direction of the magnitude is we can see 1 because of the the value of z is 1. So same thing, still working on it. So to do the integration, so first we look into parameterization as derived before. So and 1 so the circulation of integration, so now it's become w and d psi by psi over dt. So this is prime, so which is parameterization. So the parameterization, as said previously, so you have the parameterization of r, right? So until 2 pi, so this goes on straightforward, same thing, almost the same thing, but this one is ellipse is a little bit different. Okay, so still working on it. So you have this one, everything. So I just let it you go through everything given using the substitution method to solve the problem. So until you get the everything here, so we conclude that FDR so now equals to 4 pi that is okay, so that is the straightforward one. So now the example shows to use Stokes Theorem. Okay, the same thing, they give you the same answer, but here it use cross and the vector n, which is the normal vector. See, okay, so this one is just to prove. The easiest part, I think, use this one. to show. Oh, okay, sorry. So normally this example, wait a minute, sine. Okay, I just explained to you because it's already, we already solved it. So the second part is more on another way to solve it. So but the same thing we can say, the answer is same. We can say to understand, we can say, we can use which one is much easier for us to understand. So that is for the Stokes theorem. I will upload this video for your future references, and thank you. Assalamualaikum warahmatullahi wabarakatuh.